Hello everyone, welcome back to Math 0332. We're moving on to Unit 3 now. I'm Mr. Lee, and this unit primarily deals with linear equations that are more than one step. For example, on the end of Unit 2, we saw linear equations that required just the additive property equality or just the multiplicative property of equality. But here we'll do both. And I guess my best explanation about this before we talk about things is to look at x and think about what's happening to x based on order of operations. Imagine you're wrapping a present. You put it inside the box and then you wrap tissue paper around it. So if you're one of those people that unwraps presents and likes to not leave any mess by shredding through the paper, you know that you have to undo things in the opposite order that they were done. So we know x is being multiplied first and then a number is being added to it, which means if I'm trying to get x by itself, in terms of priority, you kind of reverse the order of operations when unlocking it. So generally speaking, what we're going to do is simplify as much as possible on both sides. That means if there's expressions on the left and expressions on the right that need distribution or to combine like terms, that will happen first. You get everything combined on one side. Then, when we're doing that, we'll try to get our variable by itself. If there are variables on both sides, that means moving all the things with our variable to one side and everything that doesn't have the variable to the other side. And then once we have it there, we'll be in a position to unwrap the present by going backwards in terms of order of operations. So it does kind of follow these rules. We'll always do the addition property of equality before the multiplication property of equality. So starting with number 1, 3x plus 9 equals 21. There's nothing to combine on either side because you can't combine a 3x and a 9, and 21 is already by itself. So we really get to skip step 1 and step 2. It's really more about applying the addition property of equality first, which means getting rid of something that's added or subtracted first. So we'll subtract 9 from each side to get 3x equals 12. And then from there, our goal is to get x by itself further, divide by 3 to get that x is 4. The goal is here we could plug it back in to make sure. 3 times 4 is 12. 12 plus 9 is indeed 21. So the goal here, again, is to find out what x needs to be to make this thing true. There's just more happening now than there was before. I'm going to leave 2 for you to do because I want to show one that is similar, at least. Looking at number 3, 3 is an example of where you have to do step 1 by cleaning it up, which means you need to take your 4 and distribute it on the left, take your 7 and distribute it on the right. The minus 1 will hang out for now. So this is going to give us 4z plus 12 equals 7z minus 14. And we still have that minus 1 hanging out. So now that we combine all of our like terms on either side, there's nothing to do on the left. Negative 14 minus 1 is negative 15. From here, because there are z's on both sides, I need all my z's to be in one term. The reason for this is that we're going to try to get z by itself, and if there's a bunch of z's running around, that's never going to happen. You can get it to the left or the right. I tend to go wherever the variable has more, so it will be positive. So I'm going to move my z's to the right in this case, which means everything that doesn't have a z, like this minus 15, needs to go to the left, and we'll use addition to get rid of it. To get 27 equals 3z, if you divide by 3, you get z is 9. So this is generally how this works. Now, fractions were kind of less than ideal in expressions, but in equations, we can actually do what's called clearing fractions by multiplying by the common denominator, and then we'll have no fractions left. So looking at our denominators, it's got a 3 and a 7, so 3 times 7 is 21. Which means if I multiply 21 by everything, I can make my life a little bit easier. When you're multiplying by a whole number to fractions, that number multiplies into the numerator. So this will be 21k over 3 plus 21 over 3, and there's a 1 in the denominator, so it's like nothing happens. 21k over 7 minus 21 over 3. If you picked a number that works, these should all reduce to whole numbers. 21 divided by 3 is 7, so this is 7k plus 7 equals 3k minus 7. Now, I'm not going to solve this problem from here. I'm going to leave it like this, and I'll show its solution afterwards. But once you're here, it's a lot like being here. I feel like once the fractions are gone, generally speaking, you guys are less intimidated by what's happening on the paper. Now, most of these are going to have one single solution, but there are situations where that's not true. For example, sometimes your variable will cancel when you try to move it all to one side. So linear equations really have three outcomes. Conditional outcomes are the normal ones, and the ones that you've seen up to this point, there's one answer. Identities is where when you are cleaning it up, you get the exact same thing on both sides, which means they're always equal and every number is an answer. Also, if you're cleaning up, if you end up at 0 equals 0, 0 is always equal to 0. So that will mean everything's an answer. And then sometimes though, when you're cleaning it up and your variable cancels out, you'll be left with something like 2x plus 3 equals 2x plus 5, which those two things are off by 2, or 0 equals 4, and in which case that's a contradiction. There's no way it can be true, so you have no solution. So let's see a few of these just to see what happens. I feel like one is a little bit easier to handle, so what I'm gonna do is leave one for you because it's, I think, conditional. So let's look at, say, number 2. When you distribute on both sides, you get 24y. 9 times 6 is 54, minus 3, equals 6y minus 12 plus 63. Remember, the stuff outside, nothing can happen to those. Now, the reason that we choose this problem, this is 24y minus 57 equals 6y plus 51. Now, you'll notice this looks like a typical solution because when you move everything to one side, your y's will still survive. So this isn't an example of one that is conditional or identity or contradictions. It's a conditional because you're going to get at some point y equals some number. So we can see because if we move everything to one side, this is going to end up being conditional. This one should be too, just in case you're working on it. All of the ones we have done up to this point have been conditional. Looking at number 3 though, you get 2z minus 14 equals 2z minus 6. Now you can finish this one to see what it ends up being, but it should be one answer in conditional. When you move the 2z's over to one side, you'll notice that the z's will cancel. 2z minus 2z gone, 2z minus 2z gone, and you're left with negative 14 equals negative 6. And if you ask yourself, when is negative 14 equal to negative 6, your answer should be never. Being $14 in debt and $6 in debt are never the same. If you add a few zeros to that, one feels a lot less bad than the other. So this is, when they're never equal, there's no solution. And when there's no solution, this is a contradiction. Now let's look at number 4. When you distribute, you get 15 minus 5k minus 27. This 19k doesn't have anything to do. We distribute the negative 6. You get negative 12 minus 24k. So this one simplifies into negative 5k. I'm going to bring it first, combine my like terms. 15 minus 27 is negative 12. Over here, my combined terms, 19k minus 24k is negative 5k, and the negative 12 is actually the one hanging out. So the moment that you notice you have exactly the same thing on both sides, this is a sign that these are always equal, so there's infinitely many solutions. Really, everything is a solution, and this is an identity. And this is really going to cover your first two homeworks in this section.